This is the last video you have to watch this semester, at least in my class. So the Claisen condensation involves a condensation with esters. So in this reaction, we start with some ester and we use a base like sodium ethoxide. So remember, this means that there's a sodium plus and an O ethyl with a minus charge on the oxygen. And then we follow that up with an acid workup and we get a product called a beta-keto ester. So it's beta because we're referencing the ester group. So alpha would be right next door, beta would be one more over, so there's a ketone beta to the ester, hence beta-keto ester. And this reaction is simply a nucleophilic acyl substitution reaction where the nucleophile is the enolate of an ester and the electrophile is the starting ester itself. So like we saw with the aldol, where a molecule could react with itself, the same thing's happening here. So in this, we're going to form the enolate of the ester. So our base is going to remove an alpha proton, and then that enolate is a good nucleophile, and it's going to attack a second ester molecule. So you can think of this as being like the aldol, and that half of the reactants are in the enolate form and the other half are in the electrophile form, assuming we're using a base that is not irreversibly forming the enolate. So then we get to this tetrahedral intermediate, which collapses, kicking off the OR group. Now we have this dicarbonyl intermediate, and those hydrogens are even more acidic than the starting alpha hydrogens. So that will get deprotonated with whatever base you're using in this reaction, and you get this deprotonated, doubly stabilized enolate product, which upon addition to acid, so you'll do an acidic workup, you get the neutral product. But this last step is what drives the reaction to completion. There are some important things to consider. The first is that for this reaction to work, the starting ester needs to have 2 alpha protons. And that's because that second proton removal is what drives the equilibrium forward. Also, hydroxide cannot be used as a base because you get hydrolysis. So with our carboxylic acid derivative unit, we saw that esters can be hydrolyzed back to the carboxylic acid with a strong base like hydroxide. So you want to avoid that other reaction happening. Another limitation is that the base that you're using, which is typically an alkoxide, so OR, where R is an alkyl group, that should match the OR group of the ester. Because if it doesn't, you'll get something called transesterification, which happens because in addition to forming the enolate, the alkoxide can also be doing this reaction in the background where it does a nucleophilic acyl substitution, and then you'll end up with some of the molecules having an O ethyl group and some having an O methyl. So it's much better if you just match your base to whatever the OR group is of your starting ester. Here's an animation of the Claisen condensation. So you form the enolate, and now the enolate's going to react with a second molecule of the ester so that carbon attacks the carbonyl carbon of the second molecule. And then that is going to collapse to kick off the O ethyl. And then finally, this is the driving force that acidic hydrogen between the 2 carbonyl groups gets deprotonated. Just like with the aldol, we can get crossed Claisen condensations, and these are only useful if one of the following criteria is met. One of the 2 has no alpha proton, so that's like what we saw with the aldol. So this means that only one of the 2 can be the enolate. So in this case, the molecule shown in red here doesn't have any alpha proton, so it cannot form an enolate, but this does. So this would form the enolate and attack the carbonyl carbon in the first step of the mechanism. And eventually you would get to this beta-keto ester. The second thing is you could perform a directed Claisen condensation, just like we saw with the aldol. So here you use a strong base like LDA, and you irreversibly convert all of one of your esters to the enolate form, and then you would slowly add the second ester to your flask. Just like with the aldol, where we could do an intramolecular version, we can also do an intramolecular Claisen, and it has a special name called the Dieckmann. So like with the aldol, we want to favor 4 and 6-membered rings. So in this, you would form the enolate with one of the ester groups. So for example, we could form the enolate at carbon 2, and then it's going to attack carbon 6, and that's how you end up forming this 5-membered ring. So you form a bond between carbons 2 and carbon 6. Here's an animation of the Dieckmann. So in this example, we're going to deprotonate one of the 2 ester groups, and it attacks the carbonyl of the other ester group. And then the O-ethyl is going to get lost as a leaving group. And then the final step, which is the driving force, is to deprotonate the carbon in between the carbonyl groups. The alpha position of a ketone can be alkylated, and you can do this by first forming the enolate and then adding an alkyl halide, which would then be an SN2 reaction in that second part. So you form the enolate, and then it's going to attack your alkyl halide, kicking off your halogen. So this is a typical SN2, so all of the same SN2 restrictions apply. Primary and methyl halides are the best. When you get a secondary alkyl halide, you might get some E2 competing with it, and the tertiary alkyl halides will not work. In addition, you can also get an aldol reaction competing with the desired alkylation. Therefore, it's best to use a strong base, such as LDA, to make sure that everything's in the enolate form and there isn't any of the keto form that could react with some of the enolate. So if you have an unsymmetrical ketone, you can get 2 different enolates. And which one you get will depend upon the reagents and the conditions used. So if I remove this hydrogen in blue, I would get this enolate shown here. If I were to remove either of these yellow hydrogens, I would get this enolate formed here. So this is called, the one in blue that I circled in blue is the thermodynamic, because this carbon-carbon double bond is more substituted than the carbon-carbon double bond of that enolate. And following our typical alkene stabilities, the more substituted alkene is the more stable. So the reaction pathway to form the kinetic enolate, it's easier and faster, but the resulting product is less stable, versus the thermodynamic pathway, which requires more activation energy, but ultimately the product is more stable. So you can favor one over the other by using a particular set of reaction conditions. So if you want to favor the kinetic, you're going to use LDA at cold temp, minus 78 degrees, which you can achieve in a dry ice acetone bath. And if you want to instead favor the thermodynamic, you're going to use sodium hydride at room temp. So this enolate you would form would be this, which would then attack the alkyl halide to get the R group on that side. With the thermodynamic enolate, you would form this, which would then attack the alkyl halide in SN2 to put the R group on the other side, compared to the other example. In the malonic ester synthesis, an alkyl halide can be converted into a carboxylic acid with 2 additional carbons. In this, the starting material is typically a diester, in particular diethyl malonate shown here. So the first thing in this reaction is you're going to deprotonate the most acidic proton, which is the one on the carbon in between the carbonyls. And now you have a stabilized enolate. That stabilized enolate is a nucleophile that will react with an alkyl halide in an SN2 reaction to add an R group. Then if you react this with acid and water, you can hydrolyze both of the ester groups to their carboxylic acids. Now those resulting carboxylic acid groups, when you heat, will undergo a decarboxylation to form just a single carboxylic acid. So 1,3-dicarboxylic acids, and I'm calling it 1,3 if this is carbon 1, 2, and 3, that's their relative proximity to each other. So this occurs where the pi bond of one carbonyl grabs a hydrogen of another carboxylic acid. This bond breaks, and then this bond also breaks. And you end up with an enol, which tautomerizes to the carboxylic acid. So the overall synthesis, you start with diethyl malonate, you add a base, you add your alkyl halide that you want to add, and then with acid and heat, you remove one of the two carboxylic acid groups. So the overall transformation, you had this alkyl halide, and you ended up with this carboxylic acid group attached to that carbon. You can also do a dialkylation, where you just do the whole process twice. And by doing this, you can add two R groups, and then with acid heat, you get the decarboxylated product. The acetoacetic ester synthesis is analogous to the malonate, where you have an alkyl halide and you convert it to a methyl ketone. So here, instead of having two ester groups, you have an ester and a ketone. So in the first step, you're going to make an enolate, which is then going to do an SN2 reaction with your alkyl halide. Then the acid and heat step converts this into a carboxylic acid. So before you decarboxylate, you would have this, which then upon heating gets rid of the carboxylic acid, and you end up with the product. Alpha-beta unsaturated carbonyls can be made via an aldol condensation. And if we look at these resonance forms, we see that in one of the resonance forms, there is a positive charge on that carbon, meaning that carbon is electrophilic. So in addition to the carbonyl carbon, the beta carbon, so if this is alpha, that would be the beta position, is also electrophilic, and you can have a nucleophile attack at that carbon. So whether we attack at the carbonyl carbon or the beta carbon depends upon the reagent we use. Grignards tend to do 1,2 addition, where they attack at the carbonyl carbon, and then other types of reagents, such as Dieckmann's, do the 1,4 addition, where the nucleophile attacks at this carbon. The general mechanism is that the nucleophile attacks at the beta carbon to form this enolate intermediate, which then gets protonated with an acid workup to produce the enol, which then tautomerizes to the aldehyde or ketone product. The trend is that stronger nucleophiles tend to do 1,2 addition, whereas less reactive nucleophiles do conjugate addition. Now with enolates, we often see a mixture of both types of addition. However, stabilized enolates, such as an enolate formed from a 1,3-dicarbonyl compound, we get only 1,4 addition. These types of reactions are called Michael reactions, and the donor is the name for the nucleophile that does the conjugate addition, and the acceptor is referring to the alpha-beta unsaturated carbonyl. Here are some examples of Michael donors. Notice that a lot of these are resonance stabilized nucleophiles, with the exception of the Dieckmann. And then here are examples of Michael acceptors. Notice these have a double bond in conjugation with a carbonyl, or a nitrile, or an NO2 group. So here's the animation of the Michael addition. So you start with a suitable Michael donor, and it's going to attack the beta carbon of a second molecule of the Michael acceptor. And then you get an enolate intermediate, which could be protonated. Alternatively, it could protonate the carbon, and that's how you get to the product. Singly stabilized enolates do not give high-yielding Michael additions. So for example, an enolate from a ketone. So Gilbert Stork developed a way around this called the Stork-enamine reaction. In this, you start with a ketone and some secondary amine to form an enamine. That's the first step. Enamines are nucleophilic and they will behave like an enolate, but they are less nucleophilic compared to an enolate, therefore they are good Michael donors. So the enamine will react by essentially putting electron density on this carbon, which can then attack the beta carbon of a Michael acceptor. And when you're done, you get this intermediate, which then with acid and water, the iminium goes to the carbonyl, and the enolate gets protonated and tautomerizes to the ketone. So the overall process involves 1, formation of the enamine, 2, Michael addition with your suitable acceptor, and 3, hydrolysis. So it doesn't really matter what your secondary amine here is, since it's not going to be sticking around in the product. A Robinson annulation is a 2-step process that forms a ring that involves a Michael addition followed by an intramolecular aldol condensation. So in this, you deprotonate with hydroxide that carbon, which then would attack the beta carbon of the Michael acceptor. And then after protonation, you get this product. And then you do an intramolecular aldol. So you would deprotonate that carbon, which then attacks the carbonyl to close the ring. And then the OH that you get from the aldol addition undergoes condensation to give you that carbon-carbon double bond. So just to be clear, after the aldol addition, before the condensation, you would have this addition product, and then you lose the OH group and an alpha proton to get to that double bond. Let's talk about some synthesis strategies. A lot of the reactions in this chapter are carbon-carbon bond forming, and they yield products that contain 2 functional groups. So we've discussed the aldol reaction and condensation, the Claisen and the Stork-enamine synthesis, along with the Michael reaction. And the positions of the functional groups in your product help you determine what reagents were used to synthesize it. So the Stork-enamine synthesis is great for making 1,5-dicarbonyl compounds. So notice the relationship between this carbonyl and this carbonyl, if we number each carbon, is a 1,5 relationship. Aldol and Claisen give 1,3-difunctional compounds. The Claisen gives carbonyls at 1 and 3, whereas the aldol would give a carbonyl at 1 and an OH group at 3. We've also learned 2 methods of alkylation. One is where you can form an enolate and add an alkyl group to the alpha position, and the other is where you use a Michael donor that can attack the beta position. And you could combine those 2 reactions. So for example, in this, you would add the ethyl cuprate to get that intermediate, which you could then react with methyl iodide to add a methyl group. Here is a review of all of the reactions we've looked at in this most recent unit. So we have the alpha halogenation of ketones, the HVZ reaction where we alpha halogenate a carboxylic acid, the haloform reaction where when you have a methyl ketone with hydroxide and bromine, you can convert that into a carboxylic acid. We've looked at aldol reaction, so the aldol addition gives you the hydroxyl group beta to the carbonyl, but then that can be heated and you can get the condensation product where you get a double bond between the alpha and beta carbons. We looked at crossed aldol condensations, which work best when one partner has no alpha protons. And we also saw intramolecular aldol condensation, which works best to form 5 or 6-membered rings. We looked at the Claisen condensation, which ends up with a beta-keto ester shown here. So you have a keto group beta to the ester group. We looked at crossed Claisen, and those work best when one of the partners doesn't have any alpha protons. And then we looked at the intramolecular Claisen called the Dieckmann. We looked at alkylation of ketones, and we talked about how you can form the kinetic versus thermodynamic enolate, and that will then dictate where the R group goes. We looked at the malonic ester synthesis, in which you essentially can add an R group to this carbon and then lose one of the carboxylic acids after the ester is hydrolyzed. And then the acetoacetic ester synthesis, you're adding an R group to that carbon, and again, losing a carboxylic acid. And then we finished up with Michael additions, where stabilized carbonycleophiles add to the beta carbon of a Michael acceptor, and the Stork enamine, which is a good way of converting a ketone into a Michael donor by making it into an enamine. And then finally, we looked at the Robinson annulation, where you do a Michael addition followed by an intramolecular aldol condensation. I don't have any questions for you, and this is the last video of the semester. So congratulations on finishing the videos, and we'll do some practice problems in class.